Hello, everyone. This is a talk about spherical harmonic reconstruction in Dipy. There are many models that use spherical harmonics that are widely used in diffusionmri, and you should know about it. This is a joint talk with me and Professor Maxime Descoteaux from the University of Sherbrooke. So here is an overview of this talk. We will understand what is spherical harmonics and how they're being used in diffusionmri. We will learn about single-cell model-free approaches such as analytical QBall and constant solid angle. We will understand multi-cell model-free approaches such as SOR and microstructure, and understand the main concepts behind model-based approaches using spherical deconvolution. First, let's demystify spherical harmonics. A spherical harmonic transform is simply the Fourier transform constrained by the fact that the domain is a sphere. The domain of the signal is a sphere. Spherical harmonics is simply a Fourier basis function set on the sphere. So here we see a standard signal, time is changing, it's a one-dimensional signal, and you can easily here apply the Fourier transform to get harmonics that can reconstruct the signal. Now, in our case, in diffusionmri, we use a spherical signal. So only a slice of that sphere is shown, and what you can see is that the signal is wrapping around the sphere. So if we know that, we can assume that the signal is wrapping around the sphere. So let's say if it starts from here, it will go back and connect to the same location. If we know that, we can use spherical harmonics. But let's see first what is a Fourier transform. We said that spherical harmonics is a Fourier transform for spherical domains, but what is the Fourier transform? So this is the direct Fourier transform, this integral here, and you see you provide in a function f, this is your signal, your one-dimensional signal, and then you have this carrier function. That is a complex sine wave. And if you calculate this integral, you get Fourier coefficients, which is another signal. That can go input again to another integral that then can be applied to another complex sine wave here and get back the original function, showing that there is one-to-one mapping between the Fourier transform and the Fourier coefficients. So the first is the direct Fourier transform, and then the opposite operation is the inverse Fourier transform. Now, these carrier functions here, they're not one-dimensional. They actually are complex functions, and you can visualize them like springs, where you have the time changing, and then you have the real part and the imaginary part of those signals. So what we do, we basically combine many of those springs together to recreate a one-dimensional signal. So in practice, the Fourier transform can be thought as a simple linear transformation where you have the signal here in this vector, and you can multiply the signal with each one of these columns. And in the columns, you have basically the complex sine waves for different frequencies. And if you do that, then you get the complex Fourier coefficients. You get Fourier coefficients back, which is, you can think of it again as another signal, and they have the same size. So This is simply the Fourier transform, the linear operation with a complex sine waves matrix. Now the complex sine waves, they do look like springs if you would draw them, and that is because the complex numbers that are used here, they increase the dimension in the number plane, and that creates that effect that you see here, which is fundamental for the Fourier transform. But for the spherical harmonics, we have different basis functions, but at the end they are the very similar things. You have here the low frequencies and the higher frequencies as you go. Those are orthogonal as you have with the Fourier, and they can be combined together to reproduce any function on the sphere. Now, in diffusionmri, the signal is also symmetric on the sphere, which is a fact that allows us to fit less basis functions, and therefore we need less data to fit and find the coefficients of these basis functions that, of course, in the case of spherical harmonics, they are wrapping now the sphere, they are spherical functions themselves. All right. Now, apart from spherical harmonics, there are two other important uses of the Fourier transform in MRI. First is to encode position in MRI. Basically, we create something that is called the K-space, and this is what the MRI scanner is sensing. And with the Fourier transform, we can get back images where we can understand where things are. That here is the gray matter, and here is, for example, the scalp. So that's the case. That's K-space. That's moving from frequency and phase from the spectrum, from the spectral information to actual image information. And it's used everywhere in MRI. Now, in diffusionmri, we have another use of the Fourier transform because we can build the diffusion propagator. And the diffusion propagator now uses another Fourier relation, where here you have the signal of the data, and this is now integrated with a density function, with a probability density function, and the complex exponential, the complex sine wave here. But now your main points are Q's, so that's Q space, and R becoming displacement. So this now Fourier relationship here is used extensively in diffusion spectrum imaging. And you will hear more about this from Maxime in a bit. And it allows you to build this 3D displacement distribution that is called the diffusion propagator. And what is incredible in diffusionmri, we can get a density like that for each and every voxel position. And the only requirement is to acquire many data values so that the Fourier transform is valid. And many of the efforts in diffusionmri concentrate to find some solutions to tell you like what you can do when you don't have that, when you don't have so many data sets. And we will see in a few minutes some ideas of how to move forward with that. Now, if you have this 3D density function, you can see crossings, you can see multiple configurations of crossings. And also you can, in that space now, you can either create a nice surface or build an integral that starts from the center of the propagator and moves outwards. And that is the orientation density function that we will hear more in a bit.
The holy grail of diffusion-weighted MRI is to reconstruct at every voxel this object that I call the diffusion propagator, this P of R, the diffusion propagator. So keep that word in mind because this will come in the last parts of the demonstration with all the diffusion propagator techniques. And visually, this means that at every voxel of the brain, right? So this is on the order of millimeters, let's say 2 by 2 by 2. We have this object P of R in every voxel. So this is very complex object. It's a 3D function within each voxel, right? Because this R here is a vector, and this is a radial component R, an angle theta phi. Okay, so it's doable today, but way back when diffusion started, it was impossible to reconstruct such a large 3D function at every voxel. So as you will see, we will need to make some simplifications to summarize this maybe just on a sphere, right? If we just keep here theta phi, then we're left with just a spherical function instead of a whole 3D function. And so this is the only equation, critical equation linking the signal S of Q and S0, this is the B equals 0 image, with our object P of R. So I'll change color here, but P of R here, which is our diffusion propagator. And so for the physicists out there or engineers, you see it's related via a Fourier transform. So we measure in Q space. Here Q space is actually in millimeters inverse, right? So we're measuring in frequency space, and the object that we're interested in, the P of R, is in millimeter. It's in real space. So P of R is really in the space of axons and at the scale at which we want to reconstruct features of the white matter neuroanatomy. All right, so with this equation, we see some basic math. So this S of Q, right, which is the Q space signal, and Q here is a vector in 3D. R is also it's a real space, and it's also a vector in 3D. And what you see here appearing for the first time is the ODF, which only depends on theta and phi. So this is a spherical function, where here we've integrated, sorry, so I'll remove we've integrated the radial part to have a sphere. Okay, and this will come back in some code later. So this is a 3D object, this is a 3D object, this is a 2D object. And this will have an impact on how we deal with it in Dipy. So a spherical function, SF, in a lot of the Dipy code, you'll see SF, sometimes the acronym. This is spherical function. What does it mean? Well, it simply means we have a sphere. So here illustrated by this grid, this spherical mesh, and you have a number at every point on this sphere. And you will see in my demo, we can have several points, like hundreds and thousands of points on the sphere, or just a few points. Like if you're doing DTI acquisition with 32 directions, well, you have 32 such theta phi, 32 direction. So you have a number for each of these points. So either you assign a color, or something we always do is we actually scale the radius of the sphere according to the value, right? So the value here is 0.9 and here is 0.6. And so the radial amplitude of the sphere is actually the value. So this gives us a good visual representation of the spherical function. But in a sense, it's just like a 2D image, but we don't have a pixel grid. Here we have a mesh, a spherical grid. So we're in a manifold, a 2D manifold parameterized by theta and phi. So this is a spherical function. So keep that in mind. As soon as you see SF in Dipy code, it's a spherical function. Right. So I just want to come back to this overview of the talk. So we have this link between the diffusion propagator, P of R, our signal S of Q in the 3D world. And today, you have other demonstration this week by other talks. We're taking this route here of not tissue model, so not biophysical modeling of the tissue like the NADI model or their multi-tensor model. Here we're taking the route of model-free techniques. So we're just going to play around with mathematical tools that allow us to capture the diffusion signal, the diffusion ODF, the ODF, or the diffusion propagator. And so lots of options to measure the signal Q, and we'll see a few of those options today. So either you can measure Q on a grid. This is often called DSI or Q space imaging, depending on this grid. There are radial sampling schemes that are less popular, but otherwise, when we talk about single shell, this is single shell versus multi-shell, which in a sense means single B value versus multi-B value. And so anything within this sampling scheme will have an impact on the spherical function, on the propagator, on the ODF you can extract. This is just another representation where this is DSI, this is single shell, and this is different multi-shell versions. As opposed to the first row, which is more the classical DWI for one direction, for XYZ direction, 1D Q space imaging, or the basic 6-directional DTI. Right? So today we'll mostly be focusing on single shell and a bit of multi-shell data. Right. So spherical harmonics. Why do we need spherical harmonics? Spherical harmonics are a basis function for any spherical function on the sphere. Just like sines and cosines for Fourier transforms in imaging, spherical harmonics is basically a Fourier transform on the sphere. So just a reminder for everybody, what is a basis? For instance, here you have a basis example of the canonical X, Y, Z directions in 3D, right? This is X, Y, and Z, and you can basically reconstruct any 3D point by a linear combination of red, green, blue, or X, Y, Z, right? So if you take any X, Y, Z, you can compute it by X times red plus Y times green plus Z times the blue vector. Well, spherical harmonics is the same idea. You can actually reconstruct any spherical function on the sphere just with a series of spherical harmonics coefficients. It's just a bit more complicated than the XYZ vectors because in principle or in theory, you have an infinite number of spherical harmonics, a bit like the Fourier transform. So we're going to have to truncate our basis for a specific order. So it has a mathematical formulation. You see a complex number here. It looks like a sine and cosine on the sphere with a normalization factor. Let's not focus on the math. You guys can read that on your own. But essentially, the picture here is the most powerful one. That is, given any spherical function, you can actually express it as a linear combination of a bit of a sphere, a bit of this guy, a bit of this guy, and a bit of this guy to reconstruct my crossing fiber here, for example. which would be the spherical function that I'm trying to express. So it's a way, a model-free way to reconstruct the signal, but also in a way to compress it, right? Because if you have thousands of points on the sphere, or even just 32 diffusion-weighted images, you can actually just project that on a few, in this case, 15 coefficients of the spherical harmonic spaces. And so given a certain grid and a certain sphere for a certain B value, this is single shell acquisition. So you have, you know, a diffusion weighted image for each of these points. So this would be diffusion weighted image 1 for direction 1, diffusion weighted image 2 for direction 2, diffusion image 3 for direction 3, and on like that. This would be a spherical function, right? dwi for each direction. And we could project that on a spherical harmonics basis. And the way to do that is basically to implement a Fourier transform on the sphere. So given a signal on the sphere and your basis elements, you're just trying to find the coefficients. How much of this element you need for this representation. And there's really nothing else to that. So finding the spherical harmonics coefficient of a diffusion signal, whether it's a spherical function, the diffusion data itself, an ADC or an ODF, it's always the same process. So Dipy will allow you to build this matrix. This, we often call it the SH matrix. And given any signal, will return to you these coefficients C. So, and this is actually the algorithm that's going on. There's a small regularization going on, but Dipy will build these different matrices and implement this least squared or pseudo-inverse spherical harmonics transform to provide the coefficients. And so this is a great way to go from any sphere to the basis, and then to also go to another sphere, let's say for visualization. So this will, you'll see that in my demo, but with this tool, it's easy to start from, let's say, DTI data from 32 directions, go on the spherical harmonics basis of 15 coefficients, and then project back to, let's say, 5,000 points on the sphere to have a sexy visualization. Because only this B matrix will do the trick of extrapolating data to a bigger sphere, if you wish. There's also a small, in practice, a small regularization parameter coded in Dipy. So this is why it's called the inverse, pseudo-inverse smooth. So this comes from several papers and years of research. You shouldn't really have to play with that, but it's good to know that we do actually have a small regularization just to stabilize the spherical harmonics tree. So back to the math, we saw that we could integrate the radial part. So this is just another formulation that I showed you in the past slides to transform the diffusion propagator P of R into a diffusion ODF psi of theta phi. And so, and we saw in the first part and in the demo that if we go in a region of the brain where the signal is aligned with the gradient direction, we tend to measure this donut that I showed you, right? So along the direction of axons, the actual diffusion signal is most attenuated in the orthogonal plane to it. And so this is a bit hard to grasp at first in diffusion imaging. But what you're interested in is maybe the direction of axons or how these axons are degenerating with disease. And actually the signal is maxed in the perpendicular plane. So at 90 degrees from it. And as you can see, the signal here and the signal here in the background is quite close. So this is challenging in terms of SNR and noise. And as you will learn this week, there are several ways to denoise and handle noise in Dipy. And so mathematically, I'm not going to focus a lot on the math, but there is a way to transform this donut into a shape that defines an ODF. ODF means orientation distribution function. What is the probability that I have diffusion along this direction? This is captured by the ODF in this direction. And so this Fonck-Radon transform, or another way, this was also introduced in the technique QBall imaging, is the way to do this transformation. So what's happening? So you choose a direction, you find the orthogonal plane, and you compute the integral, or the sum. So this is what this equation tells us. And that gives us a point on the ODF, this point. So you can see if my direction that I chose is not aligned with the underlying fiber population, the ODF that I get, the value of this integral, is not maximal. If on the other hand, I choose the direction exactly aligned with the fiber population and I redo this Fonck-Radon integral on the great circle, well, then this fits with the maximal value of the ODF. So David Tuck, in his famous QBall imaging paper, showed that to the world, that it was possible to transform the diffusion-weighted signal on the sphere using this radon transform. Why radon? Because it looks like computed tomography, which also does a radon transform, but now it's on the sphere, so that's why the Fonck-Radon comes into play. And so given a diffusion-weighted signal here, that we can extrapolate on a big sphere, we compute great circle integrals to get here diffusion ODFs. And this is the QBall imaging technique and model. And it's very nice because it works for any fiber crossing population, whether you have 2, 3, 1 fiber population, without assuming you just do this for several directions. So you take a direction, you take the plane, you compute the orthogonal, and do this on and on and on and on. And it works. And so what David Tuck did in his famous paper is to do this numerically. So what I was illustrating with planes and integrals, he did this with a numerical solution. What I showed in my thesis is that we could do this analytically, just using the math and the beauty of the spherical harmonic spaces. So it's possible, what usually we do is to take our diffusion signal, get the spherical harmonics coefficients, and compute the integral or the Fonck-Radon transform analytically to just get spherical harmonics coefficients of the ODF. So it's a three-step process. We load the signal on the sphere, we project the spherical harmonics, and then we transform the harmonics with an equation. So this equation is this one. You can read the paper. There's a nice proof to it. So it's just a simple math on the coefficients, right? So you get the signal, you get the C coefficients, and you apply 2 pi, the Legendre polynomial, evaluated at 0 for the specific order. And a little bit like magic, you get your solution. This just transforms the signal and performs this transformation analytically. And so you get your ODFs. And so compared with diffusion tensors that were known to be limited in crossing fibers where you get disks and very low FA regions, well, suddenly you start getting shapes of ODFs with crossing fibers. As we will see later, this is not perfect yet, but this was the first indication that, yes, there were crossing fibers in the brain and that we could reconstruct them using a relatively simple algorithm. Limitation of QBall imaging, well, these objects are quite fat and blobby. I call them potatoids here. So as you see in my code and my demo later, if we do not normalize the ODF, we get really blobby shapes. So just normalizing by min-max normalization here, you just subtract the min and divide by the ratio. You can see anatomy much better. You can see some of the crossing fibers showing up. But you see, you may get a feeling that we're not there yet, and we will get to spherical deconvolution later to really pimp this up. But lastly, it was noticed, not by me, but a few researchers, so Agaji, that the actual solution in David Tuck's paper and in my paper was lacking here the lambda squared term, or in my initial notation here, r squared. But if you add the r term here, you're adding a multi-shell dependency of the signal. You need data beyond a single B value. So this was done consciously because we wanted to do diffusion ODF and QBall imaging from a single QBall, right? The word QBall comes from Q space and a single B value in Q space. But so to add this radial dependency now on the solution, you have to assume something about the radial decay of diffusion. And that's what constant solid angle ODF does. It assumes constant ADC in time. It assumes the mono-exponential decay of the ADC. And if you assume that, well, you can actually solve the diffusion ODF with this r squared term in the equation. So this was done in parallel by Agaji and Tristan Vega to really basically give a bigger weight to diffusion signals that are further away in the propagator space. And if you do this, well, so this was the min-max normalized ODF, and now you can have the constant solid angle. So min-max normalization versus constant solid angle. So this is the CSA model, as you will see in my code. From the QBall imaging and constant solid angle, it's now possible to extract a novel metric, the measure generalized FA. And it has this formula here that, again, we can extract from spherical harmonics. So it's the standard deviation on the sphere of the ODF divided by its root mean squared. So you can actually compute that on the sphere, but it's much more elegant and fast to actually solve this equation in the world of spherical harmonics. So it's just a difference between a perfect stick, which would be 1, and 0, which would be a perfect sphere. And this is a measure of how spherical is your ODF. So the analogy of FA in the DTI world, but now for the world of QBall imaging and ODFs on the sphere. And so if you have, you know, a tighter crossing fiber here with axons, we have to keep in mind that the diffusion ODF represents the likelihood of having diffusion along a certain direction. So if I'm a water molecule here navigating, well, turns out that if I ask my diffusion ODF, what is the probability there is diffusion along this intermediate direction? Well, it's still pretty high because of this, you know, configuration. But if the question is, what is the probability of having a fiber along this intermediate direction? It's not the same question. It's a little subtlety, but it's basically 0% here, right? The likelihood of having a fiber. Here, the fibers are almost 100% in this direction and 100% this direction. And this is the difference between a diffusion ODF and a fiber ODF. And, you know, lots of book chapters and readings that you can look at to really get a clear notion and ideas about what this is. But so just to give you a brief idea, so we have a theoretical ground truth FODF, right? A perfect 100% two-directional fiber ODF. And what we in fact measure, if you actually go in the brain and you look at single fiber regions, right, where FA is super high, you know, a FA of maybe 0.8 or 0.9, so you're in a very elongated single fiber population. Well, even if you measure the ODF there, what you find is that you have, you know, a certain width to it, a certain radial diffusivity. And so you can formulate this as, you know, well, the true ground truth fiber ODF that we're looking for is actually built from the convolution between a potatoid and this ground truth ODF to give you a fat diffusion ODF from QBall imaging, for example. And this can be seen either in the signal world with donuts and weird shapes, or in ODF world via the Fonck-Radon transform. So I think it's easier to imagine for first comers in the world of ODFs, but this can be seen in the world of signal. And so if we have a 60-degree diffusion ODF, 60 degrees, sorry, and we know the response function, so we kind of have an idea of what's this blurring. So this ODF, this fat ODF that I measure in the corpus callosum or in the internal capsule where we have a single fiber, right? So this is a single fiber model. Well, if I can estimate this guy, well, I can most likely deconvolve, so inverse the process to reconstruct a sharp fiber ODF. And in fact, you know, this was developed in the mid 2000s by Donald Tournier, Flavio Dell'Acqua, myself. And so it helps in having smaller crossing angles. If you have also different volume fractions in the voxel, it helps. And now this is really the gold standard for fiber tractography because it's a sharper representation. And also as a result, it includes a model of white matter. Because for us now, white matter behaves like this cigar. And this is the object you want to give to tractography to better traverse crossing fibers and better represents white matter anatomy. So in the world of the signal, if you remember my diffusion signal in my demo, we can project it via the Fonck-Radon transform on the diffusion ODF and then deconvolve to get a sharper fiber ODFs. Or, as the original paper did, see this in the world of the diffusion signal. Now the response function is not a cigar, but the donut that we saw in my demo. And if we do deconvolve, we can reconstruct. If we're not careful, this is an extremely noisy process. So we tend to enhance high frequencies. And if we enhance fiber frequencies and we divide by things, we tend to accentuate noise. So if we don't do the constrained version, so that's hence the acronym CSD for constrained spherical convolution. If we do the unfiltered version, this is just a catastrophe. Everything here red is actually a negative number on the sphere. So this is not physical. And we see tons of green peaks that are just noise. But the constraint is just a nicer regularization process that nowadays is pretty well established. It enforces non-negativity, or it promotes it, and sparsity somehow, and you can really stabilize the numerical solution and get a sharp fiber ODF reconstruction, or FOD. And this Donald Tournier, this was the first proposition. In 2004 was the non-constrained version, and in 2007 the constrained version. So pretty much at the same time as I was doing my PhD as well. So this is part of the MRTrix package, but also now, of course, in Dipy as well. So in the world of the signal, it's the convolution between a perfect ground truth fiber ODF, a donut to produce the signal, and in the world of ODFs, like we saw before. So if you've been following what I have been saying, the key part here is this guy, the response function. How do we get this response function? Well, we have two options. Either we fix it because we have some a priori knowledge about the white matter. And this could be useful. Let's say you're doing mouse imaging or macaque imaging. The response function in a mouse or macaque is not going to be the same as in a human. But if you're doing human imaging, you might want to fix it yourself. Or another option is to estimate it from the data. And so typically in the algorithms, we have automatic response function estimators. That's what we do in Dipy. And so a good solution is to go look for voxels where the FA is high. For instance, FA above 0.7. So we know we're in single fiber voxels, and this behaves like a diffusion tensor. So we can estimate this response function and then use it in the deconvolution process. So this is what is done when it's data driven. And if we have a population study, we can take the average of the population. So for instance, when I work on Alzheimer's disease or aging, well, it turns out that this response function is a little bit fatter than in healthy 25-year-olds. So this is something to consider and to think about. But once you have this object, you can actually deconvolve. So my recommendation to you is to either fix it with a good a priori knowledge, either as the average of your group, or just manually enter it and fix it in your solution based on literature. So this is possible, and of course you'll have control over these parameters when you use spherical deconvolution in Dipy. And so it turns out that this has a tremendous effect. Even if you have low number of direction here, like 45 directions, you see here the constant solid angle diffusion ODF, right? This is a diffusion ODF. That was the best we could do so far, but that we can see is still a pretty potatoid looking in the crossing. Spherical deconvolution really has this sharpening procedure that allows us now to get all the potential crossing directions, and that will help tractography. And so now we can do these beautiful reconstruction, of the centrum semioval here, where you see a nice 2- and 3-way crossings between the corpus callosum here in red, crossing the cortical spinal tract in blue, the periodontal tract here, or the arcuate fasciculus here in green. And as a bonus, we can also start getting maps or metrics from the ODF reconstruction, fiber ODFs. So just to remind you that as opposed to a T1 where everything is white in the white matter, even though you have contrast in FA, multiple crossing fibers, the T1 information is just white. One has to be careful that now with crossing fibers, it's important to capture maybe anisotropy, but along specific directions. Okay, so this now has a new term called the fixel, right? We want a fixel-based anisotropy. So orientation anisotropy, there's no convergence on names yet, but you could very well, imagine a population study where your controls have this diffusion tensor, and suddenly your patients with degenerative disease have a more elongated tensor. So this is actually an FA going up. Well, in fact, what's happening maybe is just this green direction is deteriorating, and the blue and red direction in the ODF are fine. So this is really, really tricky. This may lead to an increased FA where actually only one fixel, this fixel, has anisotropy going down. So going beyond single shell, so now we're having, we can do static repulsion algorithms to generate multiple shells. So you can see here, we have to be careful because it's recommended and now, and it's known that it's better to have multiple shells that do choose directions that are globally uniform on the sphere. So on the left here, you have a badly sampled multiple shell acquisition. Sorry. Here. And on the right, you have the multi-shell version that's well aligned and uniform on the sphere. So now with multi-shell spherical deconvolution, there's an extra layer of complexity. Now suddenly we're going to handle all tissues in the brain. That is gray matter, right? So we're going to have to define a small spherical diffusion tensor in the cortex, because we know these are locations far from isotropic, but for diffusion it looks isotropic because we have so many crossings that it looks like a small circular diffusion tensor. We're still going to have our elongated diffusion tensor as a good model of single fibers in the white matter. And we're going to have a third compartment, which is CSF, which here is a big sphere. Right? So we have a small sphere for the gray matter, our standard diffusion tensor for single fiber populations in the white matter, and a big sphere for CSF. And the multi-shell, multi-tissue spherical deconvolution will take all these different response functions to reconstruct a white matter fiber ODF, a CSF fiber ODF, and a gray matter fiber ODF. Last but not least, we're back to square one with the diffusion propagator. So now I want to reconstruct this P of R, which is the diffusion propagator. The maths are quite complicated. I really encourage you guys to have a look at it, read the papers, but essentially a bit like spherical harmonics, there are basis functions to capture three-dimensional signals. So the same idea will apply now. We're just going to express our signal into a 3D basis, not just spherical harmonics. We will have the spherical harmonics part, but we'll also have a radial part that has these Hermite polynomials, or these single oscillator functions, simple oscillator functions that are helping us capture the behavior of the radial decay of the diffusion signal. So this is just a mathematical signal representation. That's a basis, so that's has very nice properties, but that can express the diffusion signal. So lots of literature on this topic that started quite early, but nowadays is converging in actually tools that we can use in Dipy. And so essentially, just like I told you, we can express this signal. So E of Q is actually S over S0 here as a three-dimensional basis that depends on the angular part, which is the spherical harmonics. So this is the SH part, the spherical harmonics, and a radial part, which is modeled by these 1D functions of Hermite polynomials. And if you trust me that this works, well, you can put this into the equation and actually solve the integral analytically, and you get solutions. You get a very elegant solution for the coefficient C here, but also for the features of P of R. We can reconstruct P of R itself, and then several moments, non-Gaussianity, return to origin, return to plane probability, mean square displacement, and a lot of formulas that you see actually in the papers in Einstein's formulas. But really now we can do this non-invasively with models at every location of the brain. And so as an example, we can extract this R-top feature, which is sensitive to restricted diffusion. So you can appreciate R-top almost looks like a T1 weighted image. So which highlights the restricted component of the water trapped inside axons. So we have R-top, mean squared displacement, which is the generalization of mean diffusivity, and several other metrics that we can extract. So the mean squared displacement is the generalization of mean diffusivity in the world of diffusion propagator.